Hey there, dreamer. Welcome to Hafee Sleep. Whether you're curled up in bed, sipping tea before dawn, or finally unwinding after a long day, I'm so glad you're here. Tonight, we're diving into one of the universe's most beautiful mysteries, Einstein's breathtaking vision of space, time, and gravity. Imagine floating through curved space-time as we unravel how black holes bend light, why time slows down near planets, and how the very chair you're sitting in connects you to the cosmos. All explained in cozy, easy-to-grasp stories. If stories like this help you relax, learn, or drift off to sleep, hit that subscribe button and tap the bell. Give this video a like. It helps others find this peaceful corner of YouTube. And tell me in the comments, where in the world are you watching right now? Is it 2 a.m. in London? Sunset in Sydney? Lunch break in Toronto? I love imagining our little global community of curious minds stargazing together. Let's make this journey together. Get comfy, breathe deep, and let your mind wander through the wonders of relativity. Ready? Let's begin. Close your eyes for a moment. Just feel it. That solid chair beneath you. The comforting weight of your own body. The familiar tug pulling that apple down from the tree outside. Gravity. It's the most constant companion we have on Earth. The unseen hand shaping our world, our solar system. The very stars themselves. For centuries, we thought we understood it. Sir Isaac Newton gave us a beautiful, powerful description. Gravity as an invisible force, instantly pulling masses together across vast distances. It worked. It predicted planets' orbits, explained tides, built bridges. It felt complete, solid, like the ground beneath our feet. But then, along came Albert Einstein, a patent clerk with wild hair and an even wilder imagination. He looked at Newton's elegant universe and saw cracks, tiny, almost imperceptible flaws in the cosmic engine. He asked simple, devastating questions. What is this force? How does it really work? How does it fit with the other great discovery of his time, that light always travels at the same insane speed, no matter what? The answers Einstein found didn't just patch up Newton's model. They blew the roof off the entire cosmic house. They revealed a universe far stranger, far more dynamic, far more beautiful than anyone had dared to dream. We're talking about warped time, bent space, black holes, and the very origin of the cosmos itself. Buckle up, because we're diving deep into Einstein's astonishing vision, the special and general theories of relativity. We'll see where Newton stumbled and how Einstein's genius painted a breathtaking new picture of reality. This isn't just physics. It's the ultimate cosmic detective story. All right, let's really settle into the beginning. Picture this. The universe, as understood by Isaac Newton and everyone who followed him for centuries, was a place of profound, elegant simplicity. Think of the grandest theater imaginable. But instead of plush velvet seats and a painted backdrop, this stage is utterly featureless, infinite, and completely rigid. It's made of, well, space. Absolute space. It doesn't bend, it doesn't flex, it doesn't ripple. It's just there, forever and always, a vast, unchanging emptiness stretching out in all directions. Now imagine time as the steady, unvarying beat of a cosmic drum. Tick, tick, tick. 1 second here is exactly the same as 1 second on the moon, or on Jupiter, or in a distant galaxy billions of light years away. Time flows at the same constant universal rate for everyone and everything. Absolute time. This rigid stage and this perfect universal clock. That was the fundamental framework of Newton's cosmos. Onto this vast, empty, unchanging stage, We place the actors, matter, apples, cannonballs, planets, stars, galaxies, all the stuff of the universe. Each piece of matter has a fundamental property, mass. It's the stuffness of an object. Now, Newton observed that masses seem drawn to each other. An apple falls down. The moon circles the earth circles the sun. There must be some influence acting between them. He called this influence gravity, and he proposed a breathtakingly simple law to describe it. The law of universal gravitation. It said that every single particle of matter in the universe attracts every other single particle of matter. How strong is this attraction? Newton gave us the recipe. First, it depends directly on how much mass each object has. Take two objects, double the mass of one, and the gravitational pull between them doubles. Double the mass of both, and the pull becomes 4 times stronger. More mass, stronger pull. Simple. Second, it depends critically on the distance between them. But it's not just a simple weakening. Newton discovered it weakens by the square of the distance. What does that mean? Imagine two objects separated by a certain distance, say 1 meter. The force between them is, let's say, F. Now double the distance to 2 meters. The force isn't halved. It becomes F divided by 2 squared, which is 4. So only 1/4 as strong. Triple the distance to 3 meters. The force becomes F divided by 3 squared. 9, just over 1/9 as strong. Push them 10 times farther apart. The force plummets to 1/100th of its original strength. This inverse square law is incredibly powerful. It means gravity weakens very rapidly as you move away from a source. This is why you don't feel Jupiter's immense gravity pulling you sideways right now. It's fantastically massive, but also fantastically far away. So the inverse square law makes its pull on you utterly negligible compared to the earth beneath your feet. And here's the real kicker. This force acts instantly, across any distance, no matter how vast. If the sun magically vanished right this second, Newton's law says Earth, over 93 million miles away, would immediately stop orbiting and fly off in a straight line into the cosmic darkness. The information about the sun's disappearance and the sudden cessation of its gravitational pull would travel to Earth infinitely fast. Poof, gone. Instantaneous action at a distance. It felt a bit spooky even to Newton himself, but the mathematics was undeniably beautiful and powerful. And oh my, did this law work? It was like finding the master key to the solar system. For over 200 years, Newton's universal gravitation was the undisputed king of physics. Think about it. Want to calculate the precise arc of a cannonball? Newton's gravity, combined with his laws of motion, gave you the answer. Artillery officers could now predict where their shots would land with uncanny accuracy. Want to understand why the ocean bulges twice a day, creating tides? Newton explained it perfectly. The gravitational tug of the moon, and to a lesser extent the sun, pulls the water towards it. As the Earth rotates, different parts of the ocean experience this pull, leading to the rhythmic rise and fall. The majestic dance of the planets around the sun. Newton's inverse square law predicted elliptical orbits with stunning precision. Astronomers could calculate the positions of Jupiter, Saturn, Mars, Venus, you name it, decades or even centuries into the future. Halley used it to predict the return of his famous comet. Neptune was discovered because slight wobbles in Uranus's orbit, calculated using Newton's laws, pointed to the gravitational influence of an unseen planet further out. It was a triumph of prediction. Newton's gravity seemed to govern everything from falling apples to the grandest celestial motions. It became the foundation of classical mechanics, the bedrock upon which engineering, astronomy, and physics itself were built. It felt complete, final, like humanity had finally cracked the code of the cosmos. The universe was a giant, predictable clockwork machine ticking along under Newton's elegant law. Absolute space was the stage. Absolute time was the conductor. Gravity was the invisible strings connecting everything. It was a powerful, comforting, and incredibly successful picture of reality. But even the most magnificent clockwork can develop a tiny, almost imperceptible tick, a whisper of something not quite right. For all its glory, Newton's universal gravitation had a few very small, very persistent problems. Flaws in the cosmic masterpiece. Tiny discrepancies that, like a single discordant note in a symphony, hinted that maybe the orchestra wasn't playing quite the score we thought it was. These weren't deal breakers for launching rockets or building bridges. Newton's laws were still spectacularly good for that. But for physicists peering at the very edges of precision, trying to understand the deepest nature of reality, these whispers grew louder. They were clues pointing towards a deeper, stranger truth waiting to be uncovered. The most stubborn, the most famous of these clues came from the innermost planet, speedy little Mercury. Imagine Mercury zipping around the sun, closer than any other planet, completing an orbit in just 88 Earth days. Astronomers, armed with ever more precise telescopes and centuries of careful observations, mapped its path with incredible detail. According to Newton's perfect clockwork, Mercury's orbit should be a smooth, closed ellipse, like a slightly stretched circle traced over and over again, with the sun sitting at one focus point. The point where Mercury gets closest to the sun in its orbit is called its perihelion. But here's the thing. Mercury's orbit wasn't a perfect, repeating ellipse. Over time, incredibly slowly, the position of this closest point, the perihelion, was shifting. It was gradually moving around the sun. Picture this. Instead of drawing the same ellipse repeatedly, Mercury was tracing a pattern like a very slow, very delicate rosette, or a spirograph design, where each loop is slightly rotated relative to the last. This gradual rotation of the orbit itself is called the precession of the perihelion. Now, precession itself isn't necessarily a problem. Newton's gravity actually predicts some precession. Why? Because Mercury isn't orbiting in perfect isolation, tugged only by the sun. The other planets are out there. Massive Jupiter, in particular, exerts a significant gravitational pull on Mercury, subtly tugging it over time. Newtonian physicists could calculate the combined gravitational influence of all the known planets on Mercury's orbit, and they did. Brilliant mathematicians like Urbain Le Verrier in the mid-1800s crunched the numbers. They accounted for Venus, Earth, Mars, Jupiter, Saturn, all of them. And sure enough, their calculations predicted a precession. But when they compared their meticulous calculations to the equally meticulous observations of Mercury's actual orbit, there was a gap, a tiny, infuriating gap. The observed precession was ever so slightly faster than what Newton's laws, factoring in all other planets, could explain. The discrepancy amounted to about 43 arcseconds per century. Now, an arcsecond is a tiny unit of angle. Imagine slicing 1 degree, already a small slice of a circle, into 3,600 pieces. One of those slivers is an arcsecond. 43 arcseconds is roughly the width of a dime seen from a mile away. Minuscule, almost negligible. But in the precise world of celestial mechanics, it was glaring. It was a definite, measurable anomaly. Mercury's orbit was precessing just a little bit too much. All the known actors on Newton's stage, the sun and the planets, couldn't fully account for Mercury's little wobbly dance. Where was the extra twist coming from? Was there a hidden planet, closer to the sun than Mercury, dubbed Vulcan, tugging on it? Despite frantic searches, no such planet was found. This unexplained 43 arc-seconds per century was like a tiny, persistent itch in Newton's otherwise perfectly tailored cosmic suit, a puzzle piece that simply refused to fit. For decades, it remained an unsolved mystery, a quiet challenge to the Newtonian order. While astronomers were puzzling over Mercury's orbit, physicists were wrestling with an even more fundamental mystery, one that struck right at the heart of Newton's concepts of absolute space and absolute time, the enigma of light speed. For a long time, light was thought to be made of particles, little corpuscles zipping through space. Newton himself favored this view. But in the 19th century, a revolution happened. James Clerk Maxwell, a Scottish physicist of towering genius, unified the phenomena of electricity and magnetism into a single, elegant theory, electromagnetism. His equations described how changing electric fields create magnetic fields, and changing magnetic fields create electric fields, allowing waves of energy to propagate through space. And what were these waves? Light. Maxwell showed that visible light was just one form of these electromagnetic waves, and he predicted the existence of others, like radio waves and X-rays, long before they were discovered. It was a monumental achievement. But buried within Maxwell's beautiful equations was a bombshell. They contained a constant, represented by the letter c. This constant, calculated from purely electrical and magnetic measurements, turned out to be the speed of light, approximately 186,282 miles per second. That's fast enough to circle the Earth more than 7 times in a single second. The equations implied something truly radical. This speed, c, was a fundamental constant of nature. Not just constant in a vacuum, but constant full stop. And crucially, constant regardless of the motion of the source or the observer. Let that sink in. This flew completely in the face of everyday experience and Newtonian mechanics. Imagine you're standing still by a railway track. A train roars past you at, say, 100 miles per hour. Someone on the train throws a baseball forward at 90 miles per hour relative to the train. How fast is the baseball moving relative to you standing still? Simple. 100 miles train plus 90 miles throw, now 190 miles. The speeds add up. Now imagine instead of a baseball, someone on the train shines a powerful flashlight beam forward. According to Newtonian thinking and our baseball logic, the light beam should be moving at c plus the speed of the train. If c is 186,282 miles per second, and the train is going 100 meters, which is a tiny fraction of c, about 0.015%, the light beam should be going c plus 100 meters relative to you on the platform. But Maxwell's equations said, no. Both beams of light, the one from the stationary flashlight you shine, and the one from the moving train, travel at exactly c relative to you, the observer, regardless of the train's motion. The light from the train isn't c plus train speed, it's just c. Similarly, if the train were coming towards you and shone its light at you, you wouldn't measure the light speed as c plus train speed. You'd still measure exactly c. Voice. This was mind-boggling. It violated the simple Galilean principle of velocity addition that Newtonian physics relied on. It suggested that light didn't behave like anything else in the universe. How could this be? What was light moving relative to? If speeds are relative, what defines the rest frame where light moves at exactly c? Physicists, deeply ingrained in the Newtonian worldview, proposed an ingenious solution, the luminiferous ether. Imagine this ether as an invisible, intangible, perfectly frictionless substance filling all of absolute space. It was the stage floor beneath the cosmic stage. Just as sound waves need air or some medium to travel through, light waves, being electromagnetic waves, must need this ether to ripple through. The speed of light, c, would then be its speed relative to this stationary ether. This ether would define absolute rest. If you were moving through the ether, you should measure the speed of light to be different, depending on your direction relative to the ether wind. The hunt for the ether was on. The most famous attempt was the Michelson-Morley experiment in 1887. It was incredibly clever and sensitive. Imagine splitting a beam of light, sending one part straight downstream with the hypothetical ether wind, another part cross-stream, bouncing them off mirrors and recombining them. If the Earth was moving through the stationary ether, the light traveling along the direction of Earth's motion should take a slightly different time than the light traveling perpendicular to it. This difference would cause an interference pattern, bands of light and dark, when the beams recombined. And crucially, if you rotated the whole apparatus, the pattern should shift as the arms changed direction relative to the ether wind. They built it. They set it up. They rotated it with meticulous care. They looked for the shift and found nothing, no shift, no change in the interference pattern. It was as if the ether wind didn't exist. The speed of light was stubbornly, bafflingly, the same in every direction, regardless of the Earth's motion through space. They repeated the experiment at different times of the year when Earth's orbital direction changed. Still nothing. Zip, nada, null result. It was one of the most famous failures in scientific history. This was catastrophic for the Newtonian worldview. If there was no ether to define absolute rest, what did the constant speed of light refer to? How could it possibly be the same for observers moving relative to each other? It directly contradicted the idea of absolute space. It also messed with absolute time. If simultaneity depended on light signals and light speed was constant, but relative motion changed distances, well, things got messy fast. Physicists scrambled. Some proposed desperate fixes, like the ether being dragged along by the Earth, which created other problems, or objects physically contracting in the direction of motion through the ether, Lorentz Fitzgerald contraction. These ideas felt forced, like patches on a leaky boat. So, there it was. By the dawn of the 20th century, Newton's magnificent cosmic edifice, while still incredibly useful for most practical purposes, had two significant cracks in its foundation. Mercury's mischief, that unexplained 43 arc-seconds per century in its orbital precession, defying the combined gravitational pull calculated by Newton's own laws. Light's defiance, the baffling, experimentally confirmed constancy of the speed of light for all observers, demolishing the concepts of absolute space, absolute time, and the ether that was supposed to underpin it all. The rigid stage was creaking. The universal drumbeat was faltering. The universe was whispering that there was a deeper, stranger, more dynamic reality waiting to be discovered. The scene was set. The old order was ripe for revolution. And into this moment of cosmic uncertainty stepped a young patent clerk in Bern, Switzerland, with wild hair and an imagination capable of rebuilding the universe from the ground up. Albert Einstein was about to pull back the curtain on a reality far more astonishing than Newton could have ever dreamed. So, picture this. It's 1905. Albert Einstein is 26 years old. He's working as a patent clerk, third class in Bern, Switzerland. His day job involves examining inventions for electromagnetic devices. Think dynamos, signal synchronizers, stuff steeped in the very equations of Maxwell that caused all the trouble. And in his spare time, wrestling with the cosmic headaches Newton left behind, Mercury's wobble, and especially that baffling absolute speed of light. He wasn't trying to tear down Newton's universe. He was trying to save physics, to reconcile Maxwell's brilliant electromagnetism, which demanded a constant CA, with the fundamental principle that the laws of physics should look the same to everyone moving steadily. And then, the breakthrough, not with complex apparatus, but with pure, audacious thought. Einstein proposed the Faraday special theory of relativity. It wasn't about gravity yet. It was about motion itself, about space and time, and that stubborn beam of light. He built it on just two pillars, two postulates so simple they seem almost obvious, until you follow them to their dizzying conclusions. Postulate number 1, the principle of relativity. This wasn't entirely new. Galileo and Newton understood it from mechanics. Einstein boldly declared it was universal. The laws of physics are identical in all inertial reference frames. What's an inertial reference frame? Simply put, it's your perspective when you're moving at a constant velocity, steady speed in a straight line, no speeding up, no slowing down, no turning. If you're coasting smoothly in a spaceship with the engines off, or sitting still in your living room, which is actually hurtling through space as the Earth spins and orbits, but smoothly enough, you're in an inertial frame. Einstein said, "No experiment you can do entirely within your own smoothly moving lab, spaceship, or train car can tell you whether you're really moving or really stationary." Physics plays by the same rules. Ping pong balls bounce the same. Pendulums swing the same. Light behaves the same. There is no privileged absolute rest frame. All constant velocity motion is relative. Postulate number 2, the constancy of the speed of light. This was the revolutionary one, directly tackling the Michelson-Morley null result and Maxwell's equations. Einstein stated it plainly. The speed of light in vacuum, c, is the same for all observers, regardless of the motion of the light source or the observer. It doesn't matter if you're chasing the light beam, running away from it, or standing still. It doesn't matter if the light comes from a stationary star or a headlight on a near light speed rocket. Every single observer in any inertial frame will measure the exact same value for CE, roughly 186,282 miles per second. Light speed is the universe's ultimate speed limit and its most stubborn constant. Think about how bizarre this is. Imagine two futuristic drag racers lining up on a vast straight cosmic track. Racer A is stationary relative to the starting line. Racer B is already moving at half the speed of light, 0.5 c, relative to the track. They both fire identical laser beams straight down the track. According to everyday logic, an official standing at the start line would see Racer A's laser beam zip away at c. He'd see Racer B's laser beam zoom away at c, plus 0.5 c, 1.5 c. Faster. Racer B, looking forward, would see his own laser beam leave him at CE. But Racer B, looking backwards at Racer A's laser beam coming towards him, since he's moving away from the start, would logically see it approaching at c, 0.5 c, 0.5 c. Slower. Einstein's second postulate slams the door on this logic. No. The official sees both laser beams moving away from him at exactly c. Racer B sees his own laser beam moving away from him at exactly c. And crucially, Racer B also sees Racer A's laser beam approaching him at exactly c, Not 0.5 c, not 1.5 c, always c. It defies common sense. It shreds Newton's simple addition of velocities. But this is what the Michelson-Morley experiment showed. This is what Maxwell's equations demanded. Einstein had the courage to accept it as fundamental, even if it meant rebuilding our understanding of reality from the ground up. And rebuild he did. From these two seemingly simple ideas flowed consequences that utterly shattered the Newtonian concepts of absolute space and absolute time. Forget the rigid stage and the universal clock. Einstein revealed a universe where space and time are not separate, fixed entities. They are intimately woven together into a single dynamic fabric, spacetime. And this spacetime fabric isn't rigid. It warps and flexes, depending on how you're moving through it. What you measure as space and what you measure as time depend entirely on your state of motion relative to what you're observing. Let's unpack this cosmic weirdness step by step. Consequence 1. Length contraction. Remember our super smooth, super fast train? Let's make it concrete. Imagine it's traveling at 87% the speed of light, 0.87 c, relative to the platform. Inside the luxurious dining car, you decide to play ping pong. The table is, say, 9 feet long. To you, comfortably seated inside the smoothly moving train car, everything is perfectly normal. You serve the ball. It bounces predictably. You volley. The physics feels identical to playing ping pong in your basement. The principle of relativity holds. You have no way of knowing you're moving so fast. Now, I'm standing on the platform as your train streaks past. I've got a super high-speed camera or an incredibly precise telescope that can freeze the image. I look at your ping pong table. What do I see? Here's the shock. That table, aligned perfectly with the direction the train is moving, looks shorter. To me. Significantly shorter. Not because it's squished physically in your frame. To you, it's still 9 feet. But, from my perspective, in my inertial frame on the platform, the length of the table, along the direction of its motion, is contracted. The faster it goes relative to me, the shorter it appears. At 0.87 c, that 9-foot table would look only about 4.5 feet long to me. The entire train, from my viewpoint, looks squashed along its length. This is length contraction. It only happens in the direction of motion. The height and width of the table, perpendicular to the motion, appear unchanged to me. At everyday speeds, like a car driving down the highway, this contraction is unimaginably tiny, smaller than an atom. We never notice it. But as speeds approach c, it becomes dramatic and unavoidable. Space itself is not absolute. Its measurement depends on relative motion. Consequence 2. Time dilation, the slowing of moving clocks. This one bends the mind even more. Let's equip your train car with a special clock, not a digital watch, but a light clock. Imagine 2 perfect mirrors mounted on the floor and ceiling of the train car, exactly, say, 3 feet apart. A single photon of light bounces vertically between them. 1 tick of this clock is the time it takes for the light to go from the floor mirror up to the ceiling mirror and back down to the floor again. To you, sitting inside the train car. The light path is simple. Straight up, straight down, up and down, nice and vertical. The distance it travels for 1 tick is twice the mirror separation, 6 feet. Since speed, distance, Schach's time, and the speed of light is c, the time for 1 tick is simply 6 feet. c. Now I'm back on the platform, watching your light clock through my super telescope as your train zooms past at 0.87 c. What do I see? I see the photon of light. But because the train is moving so fast relative to me, the light's path isn't vertical from my perspective. Think about it. When the photon leaves the floor mirror, the entire train and the ceiling mirror is moving sideways very fast. By the time the photon reaches the height where the ceiling mirror was when it started, the ceiling mirror has moved forward significantly with the train. So to hit the ceiling mirror, the photon has to travel diagonally forward. Click. It hits the ceiling mirror. Now it bounces down, but the floor mirror is still moving forward. By the time the photon gets back down to the level of the floor mirror has moved even further forward. So to hit the floor mirror, the photon has to travel diagonally forward again. Click. Back to the start. From my viewpoint on the platform, the light path is a zigzag, a long diagonal up and forward, then a long diagonal down and forward. It's tracing a stretched out V shape. Crucially, I see the light travel a longer distance to complete one tick than you do inside the train. The diagonal path is longer than the straight up and down path. How much longer? Using Pythagoras' theorem, we can calculate that at 0.87 c, that diagonal path is about twice as long as the vertical path you see. So, from my perspective, the light travels about 12 feet for one tick instead of the 6 feet you measure. Here comes the second postulate. The speed of light is constant for all observers. C is c. I measure the light speed as exactly c, just like you do. Speed is distance divided by time. I see the light travel a longer distance. I must therefore measure a longer time for that journey. In other words, I see your light clock ticking slower than my identical clock sitting here on the platform. At 0.87 c, I see your clock take about twice as long to tick as mine. Time itself is stretched out for the moving clock relative to my stationary one. This is time dilation. It's not a trick of the light or an illusion. It's not about mechanics slowing down. Time itself flows slower for objects in motion relative to the observer. Moving clocks genuinely run slow. The implications are staggering. If you took a super-fast spaceship journey to a star 10 light-years away, traveling at, say, 99.5% of CA, time dilation would be extreme. From Earth's perspective, the trip might take just over 10 years each way. But for you on the spaceship, because your clocks, including your biological clock, your aging, are running slow relative to Earth, the trip might only take 1 year each way from your perspective. You could travel 20 light years, and when you returned, only 2 years might have passed for you, but over 20 years would have passed on Earth. You'd have aged 2 years. Your friends and family would have aged 20 years. This twin paradox, though resolved because the spaceship twin accelerates to turn around, breaking the symmetry, illustrates the real, physical effect of time dilation. It's been confirmed countless times with ultra-precise atomic clocks flown on airplanes or orbiting on satellites. Time is not absolute. Consequence. 3. Relativity of simultaneity, the death of now. This is perhaps the most profound and hardest to grasp consequence. Einstein showed that whether two events happen at the same time depends on who is observing them. There is no universal now. Let's go back to the train, moving at high speed relative to the platform. Imagine 2 lightning bolts strike the train. One hits the very front end. One hits the very back end. Crucially, from the perspective of an observer standing exactly midway between the strike points on the platform, the 2 bolts strike simultaneously. He sees the 2 flashes of light reach his eyes at the exact same instant. Since he's midway and light speed is constant, This means the bolts had to hit the front and back at the same time for their light to reach him together. Now, you're sitting in the exact middle of the train car as it zooms forward. What do you see? The train is moving towards the point where the front bolt hit and moving away from the point where the back bolt hit. The light from the front bolt, the one the train is moving towards, has less distance to travel to reach you in the middle because you're moving closer to where it happened. The light from the back bolt, the one the train is moving away from, has more distance to travel to reach you because you're moving away from where it happened. Since light speed is constant, c, the light from the front bolt reaches your eyes before the light from the back bolt. Therefore, from your perspective inside the moving train, you see the front bolt strike first and the back bolt strike later. They are not simultaneous for you. Who is right? The platform observer who says they happened at the same time, or the train passenger who saw one before the other? Both are right. Within their own inertial reference frames, their observations are correct. There is no absolute frame-independent simultaneity. Events that are simultaneous in one frame are not simultaneous in another frame, moving relative to the first. This shatters the Newtonian concept of a universal flowing now. Spacetime is the fundamental entity. Different observers, moving at different speeds, slice this spacetime differently into their own personal definitions of space and time. Your now is not my now if we're moving relative to each other. The universe doesn't have a single shared present moment. Consequence 4. Mass-energy equivalence, E, mc2. Einstein realized that as an object speeds up, its kinetic energy increases, but special relativity puts a fundamental brake on this acceleration. Because of time dilation and length contraction, pushing an object closer and closer to the speed of light becomes increasingly difficult. Imagine trying to push a shopping cart that gets heavier and heavier the faster you try to run. From the perspective of an external observer, as the object approaches c, its inertia, its resistance to acceleration seems to increase dramatically. It behaves as if its mass is increasing. This is sometimes called relativistic mass increase, though physicists often prefer to think of it as the energy required for further acceleration becoming immense. Einstein delved deeper into the mathematics linking energy, momentum, and mass in this new relativistic framework. He arrived at perhaps the most famous equation in all of science, E more mc square. Let's break it down. Stands for energy. Mi stands for mass. Con is the speed of light in vacuum, a huge number, 186,282 miles per second. Coulombs is therefore an enormous number, about 35 trillion square miles per square second. What does this equation mean? It declares that mass and energy are two forms of the same thing. Mass is concentrated energy. Energy has mass. They are convertible. The equation tells you how much energy is equivalent to a given amount of mass, and vice versa. That C2 factor is the key. Because CE is so large, C2 is mind-bogglingly immense. This means a tiny amount of mass holds a staggering amount of locked-up energy. Think of a humble paperclip. It weighs about a gram. According to E, mc2, the energy locked within the mass of that single paperclip is equivalent to the energy released by exploding about 20,000 tons of TNT, or enough energy to power a large city for several hours. That's the power of CU. This isn't science fiction. It's the fundamental principle powering our sun and all stars. Deep in the sun's core, Nuclear fusion converts a tiny fraction of the mass of hydrogen nuclei, protons, into energy as they fuse into helium. Only about 0.7% of the mass involved is transformed, but because of C2 this releases the vast flood of light and heat that sustains life on Earth. Conversely, in nuclear fission, like in atomic bombs or reactors, heavy nuclei like uranium split, and the resulting fragments have slightly less total mass than the original nucleus. That missing mass has been converted directly into the devastating kinetic energy of the explosion or the heat energy used to generate electricity. Einstein MC2 is not just a theoretical curiosity. It's the equation that revealed the hidden energy reservoir within matter itself, shaping our understanding of the universe from the subatomic to the cosmic scale and fundamentally altering the course of human history. Special relativity was a revolution. It resolved the light-speed mystery without needing the ether. It provided a consistent framework where Maxwell's electromagnetism and mechanics could coexist at any constant velocity. It revealed a universe where space contracts, time dilates, simultaneity is relative, and mass and energy are interchangeable facets of a deeper reality. It gave us MC2, but it had a boundary. It only described physics for observers in inertial frames, those moving at constant velocity. It couldn't handle acceleration, and crucially, it didn't incorporate gravity. Einstein knew the next step. He spent another decade wrestling with how to fit gravity into this strange, flexible space-time. The key insight came from a thought so simple, so elegant, he called it the happiest thought of my life. And that thought would lead to the general theory of relativity, where gravity itself becomes the curvature of the cosmic stage. Now, let's step into Einstein's mind during those crucial years between special relativity and his grand gravity theory. He was wrestling with a fundamental question. How does gravity fit into this new, flexible space-time? How can that mysterious pull that Newton described, the force that guides planets and makes apples fall, be reconciled with the relativity of space and time, and that absolute speed of light? The answer didn't come from complex math at first, but from a beautifully simple, almost playful thought experiment. The answer came in a stroke of genius he called the happiest thought of my life. Imagine an ordinary elevator, but make it a very special one, completely sealed, no windows. The man inside can't see out, can't hear the outside world. He's cut off. Now run 2 scenarios. Scenario 1. The elevator is sitting perfectly still, right here on Earth. What does the man inside feel? He feels the familiar, comforting weight of his body pressing down onto the floor. His feet feel planted. If he jumps, he comes straight back down. If he takes an apple out of his pocket and lets go, thud. It falls straight down to the floor. Gravity is doing its thing. All perfectly normal. He feels a force pulling him down. Scenario 2. Now, magically transport this same elevator far out into the deepest, emptiest reaches of space. Utter void. No planets, no stars, no gravity whatsoever. Truly weightless. But the elevator's cable is attached to some cosmic winch, and it starts pulling the elevator upwards with a constant acceleration of exactly 9.8 meters per second squared, the same acceleration an object experiences falling freely near Earth's surface. What does the man inside feel now? As the floor accelerates upwards beneath his feet, he feels pressed down onto it, exactly like he did back on Earth. He feels that same weight. If he tries to jump, his feet snap back to the accelerating floor surprisingly quickly. Now, he takes out his apple and lets go. From his perspective inside the accelerating box, the apple doesn't float. It seems to fall straight down to the floor. Why? Because while the apple is momentarily floating motionless in space, since there's no gravity, the floor of the elevator is accelerating upwards at 9.8 meters per second square to meet it. So, relative to the man and the elevator walls, the apple accelerates downwards just like it would under gravity. He cannot tell the difference between being stationary in Earth's gravity and being accelerated upwards at 1g in deep space. Scenario 3, the flip side. Bring the elevator back near Earth, but this time, snap. The cable breaks. The elevator is now in free fall. It's falling straight down towards Earth, accelerating at exactly 9.8 ms2, ignoring air resistance for our perfect thought experiment. What does the man feel now? Weightlessness, complete and utter 0g. He floats in the middle of the car. His apple, when he lets go, floats right beside him. They are both falling together, accelerating downwards at exactly the same rate. There's no force pushing him against a floor or walls. It feels identical to floating in that gravity-free void of deep space. Again, he cannot tell the difference between being in true deep space with no gravity and being in free fall within Earth's gravity. This simple elevator scenario revealed Einstein's profound insight, the equivalence principle. It declares that the effects of gravity are completely indistinguishable from the effects of acceleration. More precisely, being at rest in a gravitational field, like standing on Earth, is physically identical to being in an accelerated reference frame in the absence of gravity, like the elevator accelerating upwards in deep space. Conversely, being in free fall within a gravitational field, like the plummeting elevator, is physically identical to being in an inertial frame, constant velocity or rest, with no gravity at all, like floating in deep space. Gravity is acceleration, or rather what we experience as the force of gravity when standing still is actually the sensation of being prevented from following our natural, force-free path, which is free fall. The chair you're sitting in right now isn't just holding you up. It's accelerating you upwards against your natural tendency to fall, just like the floor of that upward accelerating spaceship elevator. You feel the force of the chair pushing up on you, which your brain interprets as gravity pulling down. In free fall, like astronauts orbiting Earth, who are constantly falling around the planet, you feel no force because nothing is preventing you from following that natural path. This equivalence was the master key that unlocked gravity for Einstein. If gravity and acceleration are indistinguishable, then gravity cannot be some separate, mysterious force acting within the rigid Newtonian space and time. Instead, gravity must be an effect of the geometry of spacetime itself. Why? Because acceleration curves paths through spacetime. Think about it. In special relativity, in the absence of gravity, an object in free float, inertial motion, follows a straight line through the flat spacetime of special relativity, a geodesic. But if you accelerate, say, blast the rockets on your spaceship, your path through spacetime curves. You deviate from that straight line geodesic. The equivalence principle says gravity is like that acceleration. Therefore, gravity must also curve paths through spacetime. The presence of mass must curve the very fabric of spacetime, and objects simply follow the straightest possible paths through this curved landscape. Gravity isn't a pull, it's the shape of the stage. This monumental leap led Einstein, after a decade of intense mathematical struggle, to his General Theory of Relativity, GR, published in 1915. GR isn't just an update to Newton, It's a complete revolution in our understanding of gravity, space, and time. It discards the idea of gravity as a force and replaces it with geometry. The universe isn't a flat stage with actors and forces. It's a dynamic, four-dimensional fabric called spacetime, and this fabric can be warped, stretched, and curved. The core idea: mass and energy curve, spacetime. Think of spacetime as a vast, incredibly flexible trampoline. Now place a heavy object on it, a bowling ball representing the sun. What happens? The trampoline surface dips down, forming a curve, a depression around the bowling ball. This depression represents the curvature of spacetime caused by the sun's mass. Now, take a marble and roll it gently across the trampoline near the bowling ball, but not directly towards it. What happens? Instead of rolling in a straight line, the marble's path bends. It curves around the depression, perhaps even going into orbit around the bowling ball. Crucially, there's no invisible string pulling the marble towards the bowling ball. The marble is simply rolling straight ahead, following the natural contours of the curved surface. It's following the straightest possible path allowed by the curvature. That's gravity. The Earth orbits the Sun not because the Sun pulls on it, but because the Earth is moving inertially along a straight line through the curved space-time geometry created by the Sun's mass. That straight line in curved space looks like an elliptical orbit to us. These straightest possible paths through curved spacetime are called geodesics. In the absence of curvature, flat spacetime, geodesics are simple straight lines in space and time. But when spacetime is curved by mass and energy, geodesics become curved paths. Planets follow geodesics around stars. Apples falling from trees follow geodesics towards the Earth's center. Even light beams, which have no mass but possess energy, follow geodesics. In free fall, you are following your geodesic path through space-time, feeling no force. You only feel weight when something, like the ground or your chair, pushes you off your geodesic path, forcing you to accelerate relative to it. The mathematics, Einstein's field equations, describing exactly how mass and energy curve spacetime required a new mathematical language, tensor calculus. Einstein formulated his field equations. While they look intimidatingly compact, their meaning is profound. The Einstein tensor. This complex term on the left describes the geometry of spacetime at a particular point. It tells us how spacetime is curved, how much it's stretched, squeezed, or warped in different directions. It's the mathematical description of the shape of the trampoline fabric. The stress-energy tensor. This term on the right describes the matter and energy content at that same point in spacetime. It includes not just mass density, but also energy density, pressure, momentum flow, all the stuff that carries energy and can curve spacetime. It's the bowling ball on the trampoline. As a whole, Einstein field equations state that the curvature of spacetime is directly determined by the amount and distribution of matter and energy at that location. Geometry equals content. The constant g is Newton's gravitational constant, linking back to the old theory, and c is the speed of light, ensuring relativity is baked in. Spacetime tells matter how to move. Matter tells spacetime how to curve. This beautiful dynamic dialogue is encoded in this single powerful equation. It's the universe's instruction manual for gravity. Consequences, triumphs, GR's predictions, come alive. General relativity wasn't just beautiful math. It made startling, testable predictions that Newton's gravity couldn't explain. Solving Mercury's mystery. Einstein's first test was our old friend, Mercury. He plugged the sun's mass into his field equations, and calculated the geodesics planets would follow in the curved spacetime near the Sun. Unlike the perfect repeating ellipses of Newton, GR predicted that the orbits themselves should slowly rotate, that the point of closest approach, perihelion, should gradually shift around the Sun. And the amount it predicted? Exactly 43 arcseconds per century. The tiny, stubborn discrepancy that had plagued astronomers for decades vanished perfectly within Einstein's new geometric framework. It was an incredible, precise triumph. Bending starlight. Einstein realized that if spacetime is curved and light follows geodesics, the straightest paths, then light itself must bend when passing near a massive object. He predicted that starlight grazing the edge of the Sun would be deflected by a specific, calculable amount, about 1.75 arcseconds. Testing this required a total solar eclipse, so the Sun's glare wouldn't drown out the stars. In 1919, expeditions led by Arthur Eddington traveled to Brazil and Africa. They photographed the star field near the eclipsed Sun and compared it to photos taken months earlier when the Sun was elsewhere. The stars appeared slightly shifted. The measurements matched Einstein's prediction within the experimental error. When the results were announced, Einstein became a global sensation overnight. It was proof that mass warps the very fabric of space through which light travels. Gravitational time dilation. Time isn't just stretched by speed, special relativity, it's also stretched by gravity. Clocks run slower in stronger gravitational fields. Imagine two identical, ultra-precise atomic clocks. Place one deep in a valley, close to Earth's center, where gravity is strongest. Place the other high on a mountaintop, where gravity is slightly weaker. The clock on the mountain will tick faster than the clock in the valley. It gains a tiny fraction of a second over time. This isn't theoretical. It's been measured countless times. It's crucial for the Global Positioning System, GPS. GPS satellites orbit Earth, experiencing both the weaker gravity of their high altitude, making their clocks run faster relative to Earth's surface, and the high speed of their orbit, special relativity time dilation, making their clocks run slower. If engineers didn't meticulously account for both relativistic effects, GPS locations would be off by kilometers within minutes. Einstein's theories are working in your phone right now to tell you where you are. Gravitational redshift. As light struggles to climb out of a gravitational well, it loses energy. Since a light wave's energy is tied to its frequency, E, hf, where h is Planck's constant, losing energy means its frequency decreases. Lower frequency light shifts towards the red end of the spectrum. Light emitted from the surface of a dense star like a white dwarf or near a black hole is measurably redshifted compared to light emitted in weaker gravity. We see this in the spectra of stars and galaxies. Gravitational waves. Maxwell showed that accelerating electric charges produce ripples in the electromagnetic field, light waves. Einstein predicted that similarly, accelerating masses should produce ripples in the fabric of spacetime itself, gravitational waves. These waves travel at the speed of light, stretching and squeezing space as they pass by. They are incredibly weak. Detecting them required events of cosmic violence, colliding black holes or neutron stars, and instruments of astonishing sensitivity. After decades of development, the LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo collaborations achieved the seemingly impossible. The first direct detection of gravitational waves in 2015 from two colliding black holes over 1 billion light-years away. This opened an entirely new window on the universe, allowing us to hear the collisions of objects hidden from light-based telescopes. Black holes, GR's most extreme prediction. If enough mass is compressed into a sufficiently small volume, the curvature of spacetime becomes infinite at a central point, a singularity, and so extreme everywhere within a certain boundary that nothing, not even light, can escape. This boundary is the event horizon. Crossing it is a one-way trip. Spacetime is curved so severely that all possible paths lead further inwards. Black holes aren't cosmic vacuum cleaners sucking everything in from afar. They simply have a region of no return. Objects falling in follow their geodesics into the abyss. We now have overwhelming evidence for black holes, from stellar mass ones formed by collapsing stars to supermassive beasts, millions or billions of times the sun's mass, lurking at the centers of galaxies, their immense gravity shaping the orbits of nearby stars. The Event Horizon Telescope even captured the first direct image of the shadow of the supermassive black hole in galaxy M87 in 2019. What GR tells us about the universe. Einstein's theories fundamentally reshaped our cosmic perspective. Spacetime is dynamic unified. Space and time aren't separate, rigid backdrops. They are fused into a single, malleable, four-dimensional fabric, spacetime, that reacts dynamically to the matter and energy within it. It's not just the stage. It's an active participant in the cosmic drama. Gravity is geometry. Gravity isn't a mysterious force acting across a distance. It is the manifestation of the curvature of spacetime caused by mass and energy. Objects move along the straightest paths, geodesics, through this curved landscape. What looks like a pull is just the geometry of the path, the relativity of all things. There is no absolute space, no absolute time, no universal now. Distances, time intervals, and simultaneity all depend on the observer's motion and their location within a gravitational field. Space and time are relative, but spacetime is absolute. C is king. The speed of light in vacuum, c, remains the ultimate cosmic speed limit for any information, energy, or causal influence. Nothing outruns light through spacetime. Mass energy is fundamental. E ends mc squared, born in special relativity, is deeply embedded in GR. Mass and energy are interchangeable, and both are the sources that curve spacetime. The energy content of matter shapes the universe. The universe evolves. While Einstein initially resisted it, his own equations naturally described a universe that could be expanding or contracting. Edwin Hubble's discovery of galaxies flying apart forced Einstein to drop his cosmological constant, a term he'd added to force a static universe, and accept the expanding universe, leading directly to the Big Bang Theory. GR is the essential foundation of modern cosmology, describing the evolution of the entire cosmos from its earliest moments. A relativistic reality. Newton's laws are brilliant approximations for everyday life. Building bridges, launching satellites, playing baseball. But Einstein revealed the deeper, more fundamental layer. Relativity governs the extremes, the vast scales of the cosmos, the intense gravity of black holes and neutron stars, the high-speed realm of particle physics, and the incredible precision of technologies like GPS. It's the more complete description of how our universe actually works. So the next time you feel the solid ground beneath your feet, or gaze up at the moon tracing its silent arc across the sky, remember Einstein's elevator. Remember the curved trampoline of space-time. You aren't just standing on a planet being pulled down by a force. You are part of an intricate, dynamic, four-dimensional tapestry. The mass of the Earth curves the space-time around you. Your chair is accelerating you upwards, preventing you from following your natural, force-free geodesic path straight towards the Earth's center. The moon isn't being pulled by the Earth. It's cruising along a straight-line geodesic through the curved space-time geometry sculpted by our planet's mass. We live, move, and exist within Einstein's astonishing geometric universe, a universe far stranger, more interconnected, and more profoundly beautiful than the clockwork cosmos Newton imagined. It's a testament to the power of human thought that a young patent clerk, thinking deeply about elevators and the constancy of light, could unlock the secrets of gravity and reshape our understanding of reality itself. So, we've journeyed through Einstein's astonishing vision, the bending of space, the stretching of time, the revelation that gravity is the shape of the cosmic stage itself. But we have two masterpieces, Special Relativity and General Relativity. How do they fit together? Think of them not as rivals, but as two magnificent chapters in the same revolutionary book, the book that rewrote our understanding of reality. Let's unpack their unique stories and see how they weave together into Einstein's grand tapestry. Chapter 1. Special Relativity, 1905. Picture young Einstein in that Bern patent office. He's laser-focused on one cosmic headache, that baffling constancy of the speed of light, c, and how it clashes with Newton's absolute space and time. He's not thinking about planets or apples falling yet. He's thinking about light beams, fast trains, and the fundamental rules governing space and time when gravity is taking a coffee break. Imagine a vast, perfectly flat, empty region of the universe, far from any stars or planets. No gravity to curve things. Just pure space and time. This is Special Relativity's playground. Einstein built this chapter on two deceptively simple pillars. The principle of relativity. The laws of physics, all of them, not just mechanics, are identical for everyone moving at a constant velocity. No speeding up, slowing down, or turning. Whether you're sitting still in your living room or cruising smoothly in a spaceship at half the speed of light, physics works the same way inside your own little world. You can't do an experiment to prove you're absolutely moving or stationary. All constant velocity motion is relative. The constancy of c. The speed of light in vacuum is always c, 282 miles per second, no matter how fast the light source is moving, and no matter how fast you, the observer, are moving. Chase it or run from it, you always measure the same c. From these two principles, Einstein deduced that space and time aren't separate, rigid things. They are fused into a single, flexible fabric, spacetime. And this spacetime behaves in ways that utterly defy our everyday intuition, but only when things start moving at a significant fraction of c. Special relativity was revolutionary. It solved the light speed mystery. No ether needed. It unified space and time. It gave us Ebener MC2, but it had a strict boundary. It only worked perfectly for observers in inertial frames. Those lucky folks moving at constant velocity, feeling no forces, like our train passenger before it accelerates or brakes. It couldn't handle acceleration. And crucially, it had no gravity. The space-time of special relativity is perfectly flat, like a vast, empty, rigid sheet. It's the universe without bowling balls, stars, creating depressions. It describes motion beautifully on this flat sheet, but says nothing about why the sheet might be curved. That required the next chapter. Chapter 2. General Relativity, 1915. Einstein spent a decade wrestling with the missing piece, gravity. How does this fundamental force fit into the flexible space-time of special relativity? The breakthrough came with the equivalence principle, born from that simple elevator thought experiment. You can't tell the difference between being stationary in Earth's gravity and being accelerated upwards in deep space at 1 g. Gravity is indistinguishable from acceleration. This insight was the key. Acceleration curves paths through flat spacetime. Therefore, gravity must also curve spacetime. Mass and energy don't just sit on the spacetime stage, they warp the stage itself. The flat sheet of special relativity becomes a flexible trampoline. Place the sun, a bowling ball, on it. It creates a deep curve. Roll the Earth, a marble, nearby. It follows a curved path, an orbit, around the sun, not because of a mysterious pull, but because it's rolling straight ahead on a curved surface. It's following a geodesic, the straightest possible path through curved geometry. General relativity throws open the doors that special relativity kept closed. It handles everything. It applies to all observers, everywhere. Whether you're sitting still on Earth, feeling gravity, accelerating in a rocket, feeling g-forces, or floating in free fall, feeling weightless, GR describes your experience. It incorporates acceleration and gravity seamlessly. Gravity is geometry. GR banishes the idea of gravity as a force. Gravity is the manifestation of the curvature of spacetime caused by mass and energy. The Einstein field equations are the mathematical heart, stating precisely how matter-energy tells spacetime how to curve, and how that curvature then tells matter how to move along geodesics. How they fit together, the cosmic hierarchy. Think of our understanding of motion and gravity like a set of nested Russian dolls, each more encompassing and fundamental than the last. Newtonian physics, the outer doll, works brilliantly for everyday life. Apple falling, car accelerating, bridge standing, moon orbiting. It assumes absolute space, absolute time, and gravity as an instantaneous force. Its flaws appear at very high speeds, near sea, or in very strong gravity, like Mercury's orbit. It's our comfortable, intuitive layer, perfectly adequate for most practical purposes. We sent astronauts to the moon using Newton. Special relativity, the middle doll, encompasses Newtonian physics, but reveals the deeper truth when speeds approach c. It discards absolute space and time, fuses them into flat spacetime, enforces c as the speed limit, and gives us EOR's MC2. It reduces to Newton when speeds are much slower than c, but it fails when gravity is significant or acceleration is involved. Its domain is flat spacetime, inertial frames. General relativity, the innermost, fundamental doll, encompasses both Newtonian physics and special relativity. It describes all motion, constant velocity, acceleration, and gravity through the geometry of curved spacetime. It reduces to special relativity when gravity is negligible, spacetime is flat, and to Newtonian gravity when gravity is weak and speeds are slow. GR is the complete theory. It's the master framework describing the universe from the subatomic to the cosmic scale, from the gentle fall of an apple to the collision of black holes and the expansion of the entire cosmos. Special relativity, a special case. That word special is key. It's not special as in better, but special as in specific. It describes a very specific limited scenario. Physics in the absence of significant gravity, where spacetime is flat, and we only consider observers moving at constant velocity relative to each other. It's like studying motion on a perfectly flat, infinite plane, ignoring any hills or valleys. General relativity removes these restrictions. It describes physics anywhere, under any conditions, including gravity and acceleration, where spacetime can be wildly curved. When you turn off gravity in GR, set the curvature to 0, you recover the flat spacetime and all the rules of special relativity. SR is literally a special zero-gravity case within the broader framework of GR. Newton, not wrong, encompassed. So, where does this leave Sir Isaac Newton? On the shoulders of giants? Absolutely. But is he tossed aside? Not at all. Newton's theory of universal gravitation remains one of the most powerful and successful scientific achievements in history. It's incredibly accurate for an enormous range of situations. Calculating the trajectory of a Mars rover? Newton works perfectly. Designing a skyscraper? Newton's your guy? Predicting tides? Newton nails it. It's mathematically simpler and computationally far less intensive than GR for these applications. Einstein didn't disprove Newton. He encompassed him. He revealed the deeper why behind Newton's incredibly accurate how. Newton described the effect, the force, the orbits, with stunning precision based on observations. Einstein revealed the cause, the curvature of spacetime itself. Think of it like this. Newton gave us a perfect map of what gravity does. Einstein gave us the understanding of what gravity fundamentally is, the shape of the universe. Newton's tiny flaws, Mercury's wobble, the instant action problem, the clash with light speed, weren't failures. They were cosmic signposts. They were subtle hints pointing beyond the flat stage and the universal clock, whispering that there was a deeper, more dynamic reality beneath the surface, waiting for a mind like Einstein's to uncover it. Living in a relativistic universe, we navigate our daily lives firmly in Newton's comfortable domain. We don't notice length contraction in speeding cars. Our heads don't age noticeably faster than our feet. We build incredible things using Newton's laws. But the moment we step beyond the bounds of everyday speeds and Earth's gentle gravity, Einstein's universe takes over. Our GPS devices rely on both special and general relativity to place us accurately on a map. Our understanding of the universe's birth, evolution, and ultimate fate rests on general relativity. The violent collisions of black holes detected by the faint shudders of gravitational waves speak the language of curved space-time. The intense gravity around neutron stars bends light and slows time in ways Newton couldn't fathom. Even the thermonuclear fire in the heart of our sun, converting mass into energy, whispers E-nar MC2, a truth revealed in special relativity but woven into the fabric of GR. Einstein's two theories of relativity are a breathtaking achievement. Special relativity showed us that space and time are relative, malleable, and united, bound by the constant speed of light. General relativity showed us that this space-time fabric isn't passive, it's dynamic, curved by the matter and energy within it, and that gravity is this curvature. Together, they form the most successful and profound description of space, time, gravity, and the large-scale universe we have. They reveal a cosmos that is interconnected, dynamic, geometric, and far stranger than our ancestors ever imagined. The next time you feel the steady pull of the Earth, or look up at the silent arc of the moon, remember, you are not merely standing on a planet. You are an intricate part of a magnificent, four-dimensional tapestry, space-time, gently curved by the mass beneath your feet. You are experiencing Einstein's universe. It's a universe far more astonishing, more mysterious, and more wonderful than Newton could have ever conceived. It's a universe we are still exploring, still trying to fully comprehend, guided by the brilliant light of that wild-haired patent clerk's astonishing vision. Good night. Have a good sleep.